Problem-solving strategies with examples. The first one that we're going to look at is mainly to get you to see what the ideal conditions do. So our first example that we want to look at is we want to look at the voltage follower. So this is known as the voltage follower. And you'll see that sometimes it's also called the buffer amplifier. So we want to look at the voltage follower. So the goal is to show how one applies the ideal conditions of I1, I2 equal to 0, and V1 being equal to V2. A voltage follower is a unit gain amplifier. That copies a signal from one circuit to another. So we need to draw this out carefully because there's some really tricky things that you want to think about. So let's start off with this. Let's say that I have this op amp, and here is our output node, right? So this node right here is output. And we're going to have a load resistor. And a lot of the times you're going to see something where these guys are connected, and they'll say, yep, here's the common ground. This is my source. This is some resistor R. And then the key thing to a voltage follower is that there's a wire connected between V1 and V out. Now, one has to be really, really careful, because if you look at this thing, one of the things that the model tells us here is that this current I2, because that's what that node is supposed to be 0. So what you start to imagine, the way it's connected, is that the current across all the way over here, that this current right here should also be 0, and therefore V out should be connected to the ground, and therefore it's 0. Well, not so fast. We have to remember that just because we have a ground like this, it doesn't mean that the current through resistor R is the same through the resistor load. So the first thing that we should do here is that I want to make sure that I correct this. So note, this is not a correct statement. So the first thing I need to do here is that I need to redraw. Okay, we're going to redraw this circuit, and what does it really look like now? These grounds all have the same reference, but we can't account for the currents here. So now when I look at this thing, I imagine that I have a resistor with my source right here, and then I have my output over here, which has its load resistor right here. But even though they have the same ground, they don't have the same currents. So the load is different, has a different current than this resistor R. And you could see that because of the open here. And it's the sources that are really at fault here. So then if I redraw this, then my feedback line comes all the way up to here, and it looks like this. So now we could then start to look at what is going on. So the first thing that we want to do is that we want to apply the ideal model right away. So if we apply the ideal conditions, what do we actually see here? I think I'm going to copy this and just paste it down here just so that we have a good flow. So if I paste this guy right here, what we know here is that the ideal condition says that I1 and I2 are equal to 0. So let's focus on that. That means if I look at the current here, this is I1 is equal to 0. This is I2 that's equal to 0. And the first thing you got to realize is that if there's no current through that resistor, then that right there is a dead resistor. And it does not exist in the circuit. So if that's the case here, then we could then start following the nodes here. So if I was to redraw this circuit one more time, I would then say, I think I've already pasted this. So let me come in here. So what you're seeing here is that this resistor does not exist. It's a dead resistor. So it's just a wire there. That's what the current I1 and I2 being equal to 0, it kills off that resistor. So now if I start highlighting these nodes, one thing that you'll see is that this node, remember the positive node is what we call V2. And then I have this other node up here, which these two voltages must be the same. So they have the same color all the way across here. So then we see that this is V1. So when I look at this thing, remember I should have written this, so we want to redraw because that's the way it looks now. This is my circuit. So immediately what we're seeing here is that if I look at the ideal, the ideal model again, the first thing here is that by inspection, one sees that node V2 is the same as V source. Now I look at the second ideal condition. So it tells us that the input voltages must be the same. And if they're the same, that tells me then that V2, which is equal to V source, is the same as V1. But we can see immediately that V1 is a ground connected to, in this case, V out. So that is that I could then say that because V1 and V2 is equal to V source, that has to be V out as well. In other words, V out is exactly the same as the voltage source, Vs. Right? That's what that means. So when I look at this, that tells me that equal sign says that these are the same nodes. So if I was to plot this, you could see. So if I now plot the ratio of V out over V in, you could see that the gain here has a slope of 1. So if I come in here and I draw this, and this is V out, and this is V in, but V in, as you already know, is now the same as V source. That tells me then I have a slope, and when I look at that slope, we then say that the slope, which is the same, of course, as the gain, is a unit gain of 1. That's how you look at the ideal conditions when you're looking at that voltage follower. The ideal condition of I1 equals to I2 equals to 0 kills off that resistor. And then the second condition, where the voltages must be the same, tells us immediately that V1 and V2 have to be the same as the source, but because there's a wire connecting the output, it's got to be the same. Now let's bring in a second circuit, and we want to talk about the non-inverting amplifier. And of course, I want to convert this into black, and let's focus on this one. So now we want to go in and we want to apply node analysis, and we also want to apply simple circuits to do that. So here's the circuit here. It's customary to always have the negative input on the top. Do you have to do that? Of course not. But let's say that this is my circuit here. And what you're seeing is that this node, this is going to have a voltage source. And then this guy, if I start following this, looks something like this. I'm going to have some output, but then I have some resistors. And then this guy's connected to the ground, of course. And then here, this is RF, which is the feedback resistor. And this is R1. So one of the things that I said here is that if I have this, what you're seeing here is the first thing to note is the positive input is on the top. It is customary to always have the negative input on the top. This is only in the beginning. I mean, typically I don't care, but let's do what typically people do here. So let's redraw the circuit. So if I redraw the circuit here, we got to be careful again about these currents, but let's say, so this is now redrawn. So it's going to have what? I'm going to have my op amp right here. And this, look at the positive is now on the bottom. So if I follow that, look at that, the RF is the resistor that's connected from node V1 all the way to the output. So if I redraw this here, you're going to see that now I'm going to come all the way out here. I'm going to take my RF, and then I'm going to connect it to this output right here. And so this is the RF resistor right here. And remember that when I look at this VS, this really means that I have a voltage source that reads like that. So now if I look at the R1 resistor, I'm going to have to make this a little bit longer. Actually, that was fine the way I had it. Then I'm going to have my resistor R1 right here. And again, this is my ground. And then this guy is R1. So what we want to calculate is that we want to calculate V out and I out. So let me identify them. So this node right here is going to be, let's call this V out. And I'm going to say that this current right here is going to be I out. So I want to use node analysis first and then calculate those two quantities for this amplifier. So here we go. So we're going to apply both techniques to do that. So the first one I'm going to do is that I'm going to use node analysis. So we've talked about how to apply node analysis when you're dealing with op amps. So here we go. Let's do the counting. Where 1 does not count V out as a node voltage. That's the value of the source. So I'm going to come back and I want to copy this so that I could bring it down with me. So if I paste this in, here's what I'm seeing. Here's my circuit. So I'm going to start labeling my nodes. So the first node is that I'm going to label, let's say that this is V1 right here. I'm going to call this node V1. I'm going to call this node V2. And then this node over here is going to be my V out node. So let's start doing this now. So I have, you could see that I have two nodes. What are the two nodes? V1, the blue one, and the green one, V1 and V2. But I have one source, which is VS, so that gives me one node equation. Note, we know what V2 is because it has to be the same as V source. So then we could then say that this node is going to be the only node equation as we get V1 plus we have to add the ideal condition on the node voltage. So that means I have two equations. And in this case, I have two unknowns. So what are my two unknowns here? It's going to be V1 and V2. Actually, not V2, but V out. Okay, sorry about that. That was my mistake. V1 and V out. So let's go do this now. So if I look at this, again, these are the grounds right here. So here I go. So step one then tells, so I did step one, I did the counting. So now I'm going to go to step two. I'm going to apply node analysis. So I'm going to apply node analysis to V1. So if I look at that, you could see that V1 has two resistors, right? So I'm going to have resistor 1 over R1 plus 1 over RF. Then this guy is going to be V1. I have one with the ground. I have RF with V out. So I'm going to come in and I'm going to say this is minus 1 over RF. And then, of course, this is V out. And as you see here, this is one equation. Note, this is one equation with two unknowns. Which is not solvable. That's where the ideal conditions come in. So if I now go to step 3 here, I'm going to apply the ideal conditions. So if I apply the ideal conditions, the first thing I'm going to look at is I'm going to look at I1 equal to I2 is equal to 0. So let's look at the circuit. So what I'm seeing here is that I have no current here, and I have no current here. But note, there's no resistors on those lines, so it doesn't tell me anything new. So because of this, we then come back and we say, no resistors are on these lines. So there's not, we don't get anything. Now we come in and we apply the second condition. So if we apply the second condition, the first thing that we see here is that we see that V2 must be the same as the source voltage. In other words, V2 is the same as the source voltage. So that tells me then, because V2 and V1 are the same, then we have the condition that V1 must be the same as the source. Now I'm going to sub in this ideal condition on the voltages into the node equation that we just derived. And so when you look at this thing, that means I now have 1 over R1, 1 over R2, I'm sorry, RF. But now V1 is the same as V source minus 1 over RF. And then I have V out. Now this gives me one equation, one unknown, which is V out. So then if I go and get the solution for V out, we then say that V out is then going to be the combination of 1 plus RF R1 times V source. So now we know what the output voltage is. But we still need the current. So we got the voltage here, but we need the current. So to solve for the current I out, the current through R1 can now be calculated. So what do I mean by that? If you look at the circuit, let's put this circuit over here to the side. I know what V1 is. So if I focus on V1, here's what I find. So the current IR1, well, you could see that one of these nodes is V1, which we just calculated. And we saw that V1 is now the same as the source voltage. So if I now have my resistor and it's connected to the ground here, we can see that the current coming in this case, let's call that IX, this guy should be V source divided by R1, and that's R1. I know what V source is. So now what am I going to do? I'm going to follow the current. Now, follow this current to I out. So let's take this circuit like we just got, and we're going to move it down here. And the thing that you want to pay attention to is that that means I have a current IX going this way. So when I look at this current, note that this current here is iso IX because there's no current that goes through 1. So that means that current IX also comes through RF. And by inspection, we can see here that that I out current, we can then say that 1 concludes that I out has to be negative IX, which is the same as what? Minus V source times R1. Excuse me. So I've now calculated. Now we want to take the simple circuit approach. So the first thing that I want to look at is that I want to come back. I want to get that circuit that we had initially. And I'm going to say that this is our circuit right here. And let's bring it all the way down. And we want to start with a fresh circuit. So this is the circuit that we want to look at. And so what we've already done is that we've identified these nodes. and we identified this node. And the first thing that we see here, that when I look at this, we did call this node V2. We did call this guy V1. And we immediately start applying the conditions right away. Once again, we saw that this current, of course, is 0. And we see that this current going down here is 0. And of course, we still have our red node that leads to V out. So we apply the conditions immediately, right? So here we immediately apply the ideal conditions. And follow the currents. And what we see is that from the ideal condition, V1 equals to V2, this immediately tells us that V2, since it's equal to V source, is the same as V1. So in other words, we can replace V1 with V source immediately. So now what we do is that we follow the current, or follow the current of R1 to the out. So we start with the first one. So if we see that, we immediately conclude that this guy is automatically Vs, which is a known value. So let's take this in steps. So then I'm going to focus on resistor R1. And we've already done this, but we should do it again because we're trying to be independent of node. And we call this R1. We know that this is V source, and we immediately say that this is now IX. So the next resistor that we got to pay attention to is RF. Look at RF. So we know what that node is, VS, and then we have the output node. So now let's focus on resistor RF, the feedback resistor. So then I'm going to conclude immediately that if I look at resistor RF, I'm going to apply Ohm's law. So when I look at this thing, what am I actually seeing here? I have my resistor R1. We know that it has a current IX. So when I look at this node, I come all the way to right here, and there's this junction right here. And I follow the wire, and I go like, but there's no current here. I know for a fact that the current here is 0. So there's no loss of current at this point. So that means then, of course, this has to be IX. And then after the junction, we continue and we go to RF. And this RF is connected now to my node V out. So what does that mean? So when I look at this thing, as I pass this junction, I still have IX, And I still have Ix coming right through here. So now if I color in my nodes, we know that this node right here is now Vs. And so if I look at my red node, I know that this node right here is V out. So now if I apply Ohm's law, it then says that V out minus Vs must equal the feedback resistor times Ix. But we already calculated Ix. And we saw that Ix was equal to what? It was equal to V source over R1. So now if I plug this in and I solve for V out, we then see that V out has to be the combination of 1 plus RF, R1 times the quantity Vs. And you can see here that we get the exact same result. And by inspection, right, we can immediately see that if this is I out here, right, we said that this was going to be I out. We immediately conclude then that I out is then going to be equal to minus Ix, which will then be minus V source over R1. So immediately we have the results just by inspection of just applying Ohm's law in general.